should get it. Okay. Let me just check. That is off the video. There we go. Okay. Yeah, again, just to remind everyone, this is a weird classroom, so there may be a bit of a lack of space.
Very ugly.
Yeah. It's like...
Were you wearing red today?
Sorry?
Were you wearing red today?
Red jacket, yes.
Yeah?
Yeah.
Okay, I thought I saw you at the cafeteria.
Yeah, I was at the cafeteria at one point.
Yeah? Are you studying and teaching at the same time? Or what's up?
No. I just do my prep work from the cafeteria sometimes.
Oh, yeah.
Sometimes it's weird. It's one of these things. Sometimes it's easier for me to work when there's people around me making noise
Really?
than when I'm in my office quietly. Yeah.
You're not the only one.
Yeah. That's why I sometimes will do it from the cafeteria. Sometimes I'll do it from the library, like the noisier part of the library, the downstairs part of the library. Yeah.
A lot of students experience that. I go to
Yeah.
cafes and work all
Yeah, exactly. And it's something you definitely used to do it as a student. When I first got an office, I was always excited. Ooh, I have an office now. I can do my work from there. And then I'm just like sometimes, and especially because there's like, well, it's also because I don't actually, because I'm part time. I only sometimes have the office too. So yeah. But yes, no, I was definitely, yeah, I was doing the notes for next week.
Yeah, I thought you were studying too. You were so focused in.
No, that's not. I mean, I am reading the textbook. I'm trying to make sure what's covered in each section and make sure I teach the right things. That's what I'm doing. Anyways, it is time for me to start. There we go. Oh. Okay. Do I have my markers out? No, I don't. Okay. So today's Friday, January 10th, first Friday class. This is hopefully this classroom will work. It is probably possible to get it moved to a different room, but like, everyone looks like they fit in here. So it just looks a little bit smaller when I came in here, and I was worried there weren't going to be enough spots, but yeah. Everyone is in here. Yeah. So, what's on the agenda for today? Go over the agenda at the beginning as usual. I've got a couple minus points from last class. There's some folks who filled out those cards. So a couple things to go over at the beginning of class today is a review of what we covered yesterday. And then again, the main material for today is section 1.3 from the textbook, which is about what's called algebraic expressions, about polynomials, about factoring polynomials, about rational expressions with fractions of a polynomial at the top and bottom, those sorts of things. Again, the algebra today is going to be a little bit harder than the algebra yesterday was. And the stuff that today is basically the last thing that's going to be on the quiz on Tuesday. It's also the last thing that's on the web assignment, which is due on Monday. So, again, I'm pretty confident I'll be able to get through all of this. And again, if I end up being delayed, I may have to cut short some of the group problem time. But, yeah. I should get through section 1.3, and then you folks will be ready for the quiz. One thing to mention about the quiz, the way I usually do things, I usually do mightiest points before the quiz. So if there are things that come up during class today that you're like, oh, I really want extra review of that at the beginning of class on Tuesday, feel free to write it on the mightiest point card, hand it in, and I'll go over it before the quiz on Tuesday. And then otherwise I do mightiest point, I do the quiz, and then I skip right into whatever the section is on Tuesday, which will be section 1.4. Yeah. Okay. So first I'm going to go over the muddiest points from last class. The first one, rationalizing denominators. Again, that was sort of the hardest thing we talked about last class, and so there were folks who wanted to see more examples of that. So I'm going to do another example. I'm just going to just make it up. Let's say that. ab to the fourth over 4a squared. The first thing to mention, and again, when I was doing example 8 last class, I didn't do this, but if you can cancel stuff before you start rationalizing, that'll actually make things easier. So this a will cancel with one of the a's in the bottom, and we'll get this, b to the fourth over 4a. And we can take the cube root of the top and the cube root of the bottom. Now our goal here is to make this bottom into something which we can take a cube root of, something which is a perfect cube. Well, the perfect cubes are 1, 8, 27, 64, then 125. 1 cubed is 1, 2 cubed is 8. So I want to make this 4 into an 8. How do I make it into the 8? I've got to multiply it by 2. Right? 4 times 2 will give you 8. This a, I want to make it into a perfect cube. I want to make it into an a cubed. So I'm going to multiply it by a squared. A times a squared will give me an a cubed. And since I multiply by that on the bottom, I'm going to multiply by the same thing on the top. That means the top will become the cube root of 2a squared b to the fourth. And the bottom will become the cube root of 8a cubed. I should have done this over here, because I don't actually want to go much lower. I'm going to do this weird thing where I sort of do a circle around the board, and I'm going to finish it off up here. Okay, so, so here, this b to the fourth is really b cubed times b. So I can take a b cubed out of that. That cube root of b cubed will give me a b. What's going to be left inside the cube root is 2a squared b. And on the bottom, cube root of 8 is 2. Cube root of a cubed is a. So this is what you'd get once you rationalize the denominator of that guy. The second muddiest point I'm going to go over, someone was asking about the absolute value rule when we're taking the square root of something inside a square, right? I mentioned this at the very end of last class, that if you have the square root of x squared, right, what is that going to be? Well, normally you'd think the square root and the square will cancel, and this thing should just be x. This thing is only x if x is a positive number. So for example, if x is 3, we take 3 squared, we want to take the square root of 3 squared. 3 squared is 9. What is the square root of 9? The square root of 9 is just 3. So that rule, that square root of x squared is x, works for positive numbers. However, if we have a negative number, the rule is that square root of x squared is going to be the absolute value of x. Why is this the case? Well, let's say x was negative 4. Let's say I want to take the square root of negative 4 squared. Well, negative 4 squared is negative 4 times negative 4, which is 16. What is the square root of 16? It is 4. So if x is negative 4, the square root of x squared isn't negative 4, it is 4. What's the relationship between 4 and negative 4? 4 is the absolute value of negative 4. So the key thing to remember here is if we're taking something like the square root of x squared, or the 4th root of x to the 4th, or the 6th root of x to the 6th, if x is positive, which is going to be 90% of the time, if x could be negative, I will specifically say this. You know, x could be negative. So if x is positive, again, 90% of the time, we can just cancel the square root and the square and just get an x. However, if x could be negative, when we cancel the square root and the square, rather than just getting an x, we've got to put absolute value signs around it. That's just to take into account that situation of what happens if x is negative 4, or if x is any negative number. Does that make sense? Any questions about that before we move on? So the key thing is when you're simplifying square roots, if I don't tell you otherwise, you can assume that x is positive, you can use this rule. Right? The square root and the square will cancel. If you're simplifying square roots and I've told you that x could be negative, then you've got to use this rule. Take the absolute value of it. And the square root and the square cancel, you get the absolute value of x. I'm trying to think if I can think of an example of a problem where this would come up in. I can't think of one yet. Anyways, I will come up with later once we talk about next week. I'll come up with an example of a problem where if you do it this way, and x turns out to be a negative number, it doesn't work. So, yeah. Okay. So let's move. Oh, this is not a keyboard for my computer. It's a keyboard for the other computer. Okay. Okay. So we're moving on now to section 1.3, which is called algebraic expressions. And I just realized I don't have a time piece up here. So let me pull out my. So algebraic expressions, again, polynomials are the simplest type of algebraic expression. That's what we're going to be talking about first. So polynomials are what you get when you expand this thing. Right? Polynomials like x squared plus 2x minus 3. Example of a polynomial. So how many people here feel confident that they could expand this? How many people here feel like they would have difficulty expanding this? Good. Again, should be fairly straightforward. Expanding polynomials is the easiest thing you can do with polynomials. So I'll go through this section fairly quickly. What's going to be more difficult is some stuff that's going to come up later. So, polynomial are things like this guy. 3x cubed plus 2x squared minus 4x plus 6. Or this guy. X to the 7 minus x to the 6 plus 4x squared plus 1. There's some terminology about polynomials which will be important. Knowing what the terms of a polynomial are, knowing what the coefficients of a polynomial are will be important. And also that the degree of a polynomial just means whatever the highest power of x is. So if I have this guy, 3x cubed plus 2x squared minus 4x plus 6, the terms are 3x cubed, 2x squared, minus 4x, and 6. So I say this polynomial has 4 terms, right? Talk about coefficients, I could say something like the coefficient of x squared is 2. 2 is the number in front of x squared, so 2 is the coefficient of x squared. The degree of the polynomial is the highest power of x. The degree of this polynomial is 3, which means it's what's called a cubic polynomial. I'm not going to be testing you on the terminology of quadratic, cubic, quartic, that sort of stuff, but knowing what I mean when I say the degree of something, knowing what I mean when I say the terms, knowing what I mean when I say the coefficients, important terminology. Okay. Any questions about that terminology before I move to the next slide? Okay. Again, so a lot of this should be review. So expanding polynomials, again, is the simplest thing to do with polynomials. There's 2 steps to expanding. You've got to multiply polynomials out, and then you've got to collect like terms. When you're multiplying polynomials, you've got to take each term in the first polynomial and multiply it by each term in the second polynomial. And again, when you're collecting like terms, we must remember that 2 terms can only be combined if they're the same power of every variable. So if there's like x squared y and there's yx squared, you can't combine those 2. Oh, no, x squared y and yx squared. Sorry, x squared y and xy squared. You can't combine. This is what I said. These are 2 different ways of writing the same thing. X squared y and yx squared, I just put them in a different order. What I meant is x squared y and xy squared. These 2 guys you cannot combine. This is a power of 2 on x and not 1 on y. This is 1 on x and 2 on y. They're different things. Yeah. Okay. So, the first example here I want you to expand is something squared. It's 5x minus 4y squared. Again, just to mention, when you're squaring a polynomial, it's the same thing as multiplying it by itself. What you are not going to do, you are not going to take the 5x and square it and the 4y and square it and just do that. Again, it's a common mistake for people to make. If I write a minus b squared, I've seen so many people write a squared minus b squared. It is not a squared minus b squared. You have to expand it like this. Take the 5x minus 4y and multiply it by another 5x minus 4y. When you do this, you take 5x times 5x gives you 25x squared. 5x times negative 4y gives you minus 20xy. Negative 4y times 5x gives you another minus 20xy. And then 4y times 4y gives you 16y squared. So that's what you get when you expand that polynomial. Oh, now I need to collect like terms. Sorry, that's what you get when you multiply it out. Then I need to collect like terms. Minus 20xy, minus 20xy. If you combine those, you get minus 40xy. The 16y squared, we can't combine with anything. Same with the 25x squared. We can't combine either of those with anything. Any questions about how I expanded that guy? Again, I picked example with something squared just to remind people that that common mistake of just squaring the first thing and squaring the second thing doesn't work. Yeah. Okay. The last thing in this 1.3.1 section is a bunch of product formulas. Again, these are formulas that are useful for expanding things. One thing to mention about when I expand this, 5x minus 4y, I could have done it in one step if I had known this formula here. This formula here says that x plus y squared will be x squared plus 2xy plus y squared, or x minus y squared will be x squared minus 2xy plus y squared, right? Here the x is 5x, the y is 4y. So this x squared term at the beginning would be 5x squared, which gives you 25x squared. The minus 2xy will be minus 2 times 5 times 4. 2 times 5 times 4 is negative 40. Negative 2 times 5 times 4 is negative 40 xy. And similarly, that y squared at the end will just be 16y squared. Again, you don't have to do things using these formulas if you don't want to. Just do it the way I did it on the board. But those formulas are useful, and hopefully you've seen those before. The first two I'm pretty confident that you should have seen before. X plus y times x minus y is x squared minus y squared. And this one for x plus y squared, and for x minus y squared, what that gives you. The last three are a little bit more complicated, and they're for cubes. So we have x plus y all cubed is going to be x cubed plus 3x squared y plus 2xy. Oh, this would be a 3. Sorry. I'm going to write those guys out again. Just a couple of typos left, right, and center. That's what we get. So x plus y cubed should be this, with 2 3s. X minus y cubed should be the same thing with 2 3s. Again, because those two formulas are very similar, we oftentimes write them like this, with a plus or minus here, a plus or minus here, a plus or minus here, which means this one's a plus, this one will be a plus, and this one will be a plus, this one's a minus, this one will be a minus, and this one will be a minus. These last two formulas here are mostly going to be useful when we're factoring things that look like x cubed minus y cubed, and x cubed plus y cubed. And I think I should be doing an example of those at some point. Okay. So again, those formulas, you can memorize them if you want to. You can just do it sort of the long way, like I did it here if you want to as well. Any questions about that? Again, because this stuff should be reviewed, I'm going through it fairly quickly. Okay, so the next section, 1.3.2, is about factoring polynomials. So if you got a polynomial like this guy, 3x squared minus 5x minus 2, how would you go about factoring it? How many people feel they'd be confident factoring that guy? How many people feel like they have no idea how to factor that guy? Anyone has no ideas? How many people think they might be able to but aren't sure? No one? Okay. I think it's just a lack of hands, perhaps. Anyways, Factoring is more difficult than expanding, but again, it should be stuff that you've done before, and this section should be reviewed again. So I'm just going to quickly go over the different types of factoring that there are. One example of each type. So the first and easiest type of factoring is taking out a common factor. If you're a polynomial with multiple terms and it's the same thing that goes into every term, we can always take that same thing out as a common factor. And again, sorry, I kind of skipped this first paragraph. The first paragraph is saying that when you're factoring something, your goal is to take a polynomial that's written out like this and turn it into something like this, something times something else. So our goal is to go from what's called a sum to a product. Things added together to things multiplied by each other. So if I have something like x to the fourth minus 6x cubed, right, there's a thing that goes into both terms. What that thing is x cubed. I take an x cubed out of the first term and left with an x. I take an x cubed minus out of the second and left with a 6, right? X cubed times x minus 6. Again, this is the easiest method of factoring. A lot of people tend to forget this when dealing with harder problems. Forget that they can factor things this way. We'll see x to the fourth minus 6x cubed and be like, it's an x to the fourth in there. I have no idea how to factor it. And the answer is you factor it by just pulling out an x cubed, by looking for the common factor of the two terms. So, yeah. Any questions about this sort of factoring? Okay. Next, more difficult type of factoring is called factoring by grouping. Factoring by grouping works when you have polynomials with 4 terms in them. And when you're factoring things by grouping, what you do is you look at the first 2 terms, try to take a common factor out of the first 2 terms. Look at the last 2 terms, try to take a common factor out of the last 2 terms. And then take a common factor out of what's left. So an example of factoring by grouping is this guy here. Here we have 5x cubed plus 10x squared minus 20x minus 40. So we look at these first 2 terms. What do they have in common? Well, they both have a 5 in them, right? 10 is 2 times 5. They both have an x squared in them. So we can take the 5x squared out. What's left? We take 5x squared out of x cubed is going to be x. We take the 5x squared out of 10x squared, what's left is going to be a 2. Then we look at the last 2 terms, minus 20x minus 40, and say, what do they have in common? Well, they have a negative 20 in common. They both have negative 20 in them. We take a negative 20 out of negative 20x, we get an x. Take a negative 20 out of negative 40, we get 2. Now, the key thing, what makes this factoring by grouping work, is that this thing and this thing are the same. If they're not the same, the grouping won't work. And because it's the same, I can take out that x plus 2 as a common factor. What's going to be left is going to be a 5x squared minus 20. Now, one thing to mention about this, let's talk about it a little bit later, is that this thing here, that 5x squared minus 20, will actually keep factoring. This piece here, you could actually keep doing more work to keep on factoring this piece. I'm going to do that later, but yeah. I just want to show an example of how this grouping method works, right? Take the first 2 terms, take something out, take the second 2 terms, take something out. If those 2 somethings are the same, that can come out as common factor, and what's left is going to be this guy and that guy. Any questions about this grouping method? Is there anyone here who has not seen this grouping method before today? Good. I know there's some places where this is not taught. At least there were when I was in high school. So it was possible to graduate high school without learning this back in my day, and that's, yeah. Anyways. Okay. The next factoring methods I'm going to talk about are the ones for dealing with what are called trinomials. Trinomial is just a fancy word for a polynomial with 3 terms. Tri means 3, nomial means terms. So if the first term is x squared, factoring them is easy. And I'm pretty confident that if you made it through high school, you should know how to factor things with an x squared as the first In that case, you should find two things that add to give the middle term, multiply to give the last term. Middle coefficient in the last term. So example 4 here, we've got x squared minus 3x plus 4. What we need is we need two numbers that multiply to give you negative 3, add to give you positive 4. Wait a second. We'll make this a minus 4. The reason is if it's a plus 4, it actually doesn't work. There are no two numbers that multiply to give you negative 3 and add to give you positive 4. But there are two numbers that multiply to give you negative 3 and add to give you negative 4. Sorry, multiply to give you negative 4 and add to give you negative 3. They're minus 4 and positive 1. So again, if you've got a trinomial, 3 terms, where the first term is x squared, factoring them is easy. Just find those two numbers that add to give the middle, multiply to give the end. If the first term isn't x squared, it becomes more difficult. Now there's a couple ways of approaching the ones where it isn't x squared. The way I like to use is what I do is I take the product of the first term and the last term, first coefficient and the last term, so the thing in the front and the thing at the end, multiply those together, see what number that is, take the middle term, see what number that is, find two things that add to give you the middle term and multiply to give you the end, and then once I have those two numbers, I use them to actually split up that middle term. And I'll show how to do this in the example I'm about to do. There are other ways of factoring these guys, and if you know another way of factoring them, I believe the way that's most often taught in high school is completely different from the way I do it. Go for it. Do it that way. My way of doing it is not the only way of doing it, but the other ways should give you the same answer. If they don't give you the same answer, you probably have a method that doesn't work. So here, I have 9x squared plus 24x plus 16. If I want to factor this guy, what I do is I take the 9 times 16. What does that give me? 9 times 16 gives me 144. So I want two numbers that multiply to 144 and add to 24. Those two numbers turn out to be 12 and 12. So then, this middle term can become a plus 12x plus 12x. So once I find those two numbers, right, 12, I shouldn't write there. So what I'm thinking when I'm doing this, I'm thinking I want two numbers that add to give me 24 and multiply to give me 144. Those two numbers turn out to be 12 and 12. Right? Once I find those two numbers, that's what I use to split up that middle term. 24x is 12x plus 12x. And then I perform grouping. What's the common factor? The first two terms is 3x. What's left is a 3x plus 4. What's the common factor? The last two terms? Last two terms are the common factor of 4. And what's left is 3x plus 4. And since these both have a 3x plus 4 in them, I can take out the 3x plus 4 as a common factor. And what's left is going to be 3x plus 4. By the way, you'll notice that both the factors in this one turned out to be the same thing. You had 3x plus 4 twice. What that means is that this polynomial is what is called a perfect square. And I will talk about that a little bit on the next slide. The idea is that because it was a perfect square, I actually could have factored it using one of those formulas that I went over back a couple slides ago. Any questions about how I factored this guy? I know this method might be new to people because I think the one that's usually taught in high school is different. If you remember the one that's usually taught in high school, feel free to use it to factor these guys. If you don't, this method should work. Yes?
One method that should be useful, I know our last professor expected us to look at it and do it.
Yeah, no, I know. I was gonna say that's the other. There's three ways of doing it. There's one that's done in high school, which is like you take the first term and you multiply it by the last term, and you make a thing with an x squared in front, and then you have to remember to move it back at the end. And everyone always forgets to move it back at the end, which is why I don't teach it that way. Again, there's sort of the guess and check approach, where you just like, okay, let's figure out what these two numbers are, see them, multiply them out to get that. And then there's this approach, which is called the grouping method. It takes more time to do things this way, which is one of the reasons that a lot of people don't teach that, but it works. It will always work. Find two numbers that multiply to give you this times this, and add to give you the middle term. Use those to split up the middle term. Okay. Any other questions before I move on? Okay. So the last type of factoring I'm going to talk about is factoring using formulas. And this is usually what you're going to do when you have more complicated polynomials, things that have like an x to the fourth in them, for example. It's very difficult to factor without a formula. So the formulas that I'm going to be talking about are these formulas back here, like the formulas on this product formula slide, which are also given in the textbook. For example, let's go back to that product formula slide for a second. If I wanted to factor this guy using the formula, I could look at this polynomial and be like, aha, this polynomial sort of looks like this. This 9x squared is something squared. The 16 is also something squared. And this middle term, the 24, so the 9x squared is 3x squared. The 16 is 4 squared. And that middle term is 2 times 3x times 4. 2 times 3x times 4 will give you 24x. So that polynomial does fit this formula, so I can factor it as something, x plus y squared. The x I said was 3x, the y was 4. That's why it's 3x plus 4 squared. So anyway, I could have done that one using that formula if I wanted to. Actually, I'm just going to go here and go back a slide. And sometimes also, if we're trying to use formulas to factor things, if there's a common factor we can take out, do that first before you attempt to use the formula. Example 6 here is one that uses a different formula. Example 6 looks like x to the 8 minus 16. So again, x to the 8, pretty big polynomial. You'll think it might be difficult to factor. What we're going to do when we do this is we're going to look at the first term and look at the last term and be like, this first term is something squared, right? This first term is x to the 4th squared. The last term is also something squared. 16 is 4 squared. And there is a formula that says x squared minus y squared is x minus y. Oh, sorry, make some more space for that. X squared minus y squared is x minus y times x plus y. Again, that's one of the formulas that was on that slide a few slides ago. So here I have my x is x to the 4th, my y is 4. So this is going to factor as x to the 4th minus 4 times x to the 4th plus 4. Now we can actually factor this even further. The x to the 4th minus 4 is still something squared minus something else squared. We can think of it as x squared squared minus 2 squared. That will give you x to the 4th minus 4. So it'll factor again using this formula as x squared minus 2 times x squared plus 2. The other thing I want to mention, the x to the 4th plus 4 will not factor. There is no way of factoring a sum of two even powers. That guy's just going to stay the way it is. And then one last step, this guy will still factor, that x squared minus 2. And the reason is that 2, so I'm just going to copy this out again. Actually, no, first I'm going to say the x squared minus 2 is really x squared minus the square root of 2 squared. Right? 2 is actually the square root of 2 squared. So this thing is still x squared minus y squared for some x and some y. So it will factor then as x minus the square root of 2 times x plus the square root of 2. And then we're still going to have those guys. X squared plus 2 and x to the 4th plus 4. So the idea is that sometimes factoring polynomials which start off fairly complicated can take a fairly long procedure to do. And sometimes in the factors we'll end up with weird numbers like the square root of 2 in there. And that's not a it's not a problem in the sense that it just shouldn't stop us from factoring things. It is weird. It will cause problems in other senses, like how do I evaluate that thing? How do I plug a number in for x and figure out what it equals to? But it shouldn't stop us from actually doing the procedure of factoring. Any questions about this example? Yes? Oh, because there's no formula for x squared plus y squared. There's only one for x squared minus y squared. There is another reason for this, which I will talk about later. Or actually, no, I can say it now. I don't know, for those who have seen like quadratic polynomials before, I don't know if you remember, when you factor it, you get the x-intercept, you get the zeros, the place where it crosses the x-axis. If I graph this guy, it does not cross the x-axis, which is another reason explaining why I can't factor. If you graph it, it's up here. Anyway, so for those who sort of understand that sort of aspect of the relationship between factoring things and their graphs and where the graphs cross the x-axis, that's the other explanation to it. But again, if you don't understand that yet, that's okay. I'm going to be covering that like in a couple weeks. So, yeah. Yeah. Okay. So that, let's check the time. Okay, good. Yeah. I'm still mostly on time. So the next section, 1.3.3, deals with what are called rational expressions. Basically, I mean 1.3.3 and 1.3.4 are both sort of about rational expressions. They're both about fractions which have x's on the top and the bottom, what are called rational expressions. The difference really between the 1.3.3 stuff and the 1.3.4 stuff is this stuff is sort of rational expressions in general. The 1.3.4 stuff is some specific problems you'll see in calculus, some specific algebra tasks that you will need to do with these rational expressions, they call them. So, okay. So our goal here is to be able to simplify things like this. X plus 2 over x minus 2 plus x over x squared minus 4. How many people feel like they would be confident simplifying something like that? Anyone? One? How many people are totally confused by that? Anyone? How many people? Is there anyone who had? I know. I'm pretty sure. You should. I was going to say you should all have seen that before. Is there anyone here who hasn't seen that before or doesn't remember it at all? Okay. Anyways, this is sort of one of the more difficult algebraic tasks. Is putting things like this together. For those who remember this, the key thing in something like that, when you're adding rational expressions, is to find what's called the least common denominator. If you remember least common denominators, that's what you're going to be doing here. And again, I'll spend a little bit more time on this section because this is harder than a bunch of the stuff that's come before. So, a rational expression is just a fraction of the polynomial on the top of the numerator, a polynomial on the bottom in the denominator. So when we're simplifying rational expressions, our goal is to factor the top, factor the bottom, and then once they're factored, things can cancel. Just one thing to mention about canceling using fractions. You are not allowed to cancel things from the top and bottom of fractions which are added to or subtracted from other things. These a's here cannot cancel. And the reason is because this a is added to a b, and this a is subtracted from a b. Things that are added or subtracted, terms on the top and bottom of fractions, terms is the word for which is added or subtracted, are not allowed to cancel. However, these a's are allowed to cancel. Why? Because these a's are multiplied by things in the top and bottom of fractions. So things that are multiplied by other things are allowed to cancel. And that's the reason we have to factor the top and bottom before canceling. Because when we're factoring things, we're writing it as something times something else, times something else. And once these things are multiplied together, then they can cancel. If they're not multiplied together, you're not allowed to cancel them. Now, when we have something even more complicated, when we have entire rational expressions that are multiplied by each other, like if we have one fraction times another fraction, just multiply the things on top, multiply the things on the bottom. If we have one fraction divided by another fraction, we always flip the second one and multiply it. Again, those are the basic rules for multiplying fractions, but some people get confused when the fractions of algebra are done. So, We'll see that with example 7 here. Here we have one rational expression divided by another rational expression. So in example 7, what we're trying to simplify is 5a squared plus 12a plus 4 over a to the 4th minus 16 divided by 25a squared plus 20a plus 4 over a squared minus 2a. Now, this is a particularly difficult example. This will take me a fair bit of time to do. And I just want to mention that before you do it. Like, you're not going to see something this hard on the quiz, but you might see a problem that's like this with slightly simpler things at the top and bottom of these fractions. So, in this example, our goal is always to factor everything and then see if we can cancel things. So let's say I want to factor 5a squared plus 12a plus 4. I'm just going to write that over here, and I'm going to sort of show the procedure for factoring it. And I'm sort of going to do that with each part. So we want to factor this guy. Well, we want 5 times 4 is 20. We want two numbers that multiply to 20, add to 12. Those two numbers are 10 and 2. What that means is that the middle term can split up as 10a plus 2a. And then these first two terms have a common factor. That common factor is 5a. What's left is a plus 2. The last two terms have a common factor. That common factor is 2. And what's left is a plus 2. And then both these things have an a plus 2 in them, that a plus 2 is going to come out. We have a plus 2 times 5a plus 2. So that's how that first guy's going to factor. This second one, you can still do it that way if you want, but when you're factoring this second one, the 25a squared plus 20a plus 4, actually I'm going to do that here. I don't want to write that one yet. When we're factoring this guy, the key thing is this 25a squared is 5a, all squared. The 4 is 2 squared, and this 20a is 2 times 5a times 2. What that means is we can factor that using the x plus y squared formula. This will factor as 5a plus 2 squared. Sorry, does that help? Okay, so I factor the top here, I factor the top there. Oh, sorry, no, I'll leave this on in case people are copying it down. And over on this side of the board, I am now going to factor the a to the 4th minus 16. If I want to factor that guy, a to the 4th is a squared squared, 16 is 4 squared. So it's going to factor as a squared minus 4 times a squared plus 4. Again, that's using the difference of squares formula. The x squared minus y squared is x minus y times x plus y. A squared minus 4 is itself a minus 2 times a plus 2 using that same formula. And the a squared plus 4 will not factor. Again, the sum of two squares is never going to factor. So that's what we're going to get on the bottom of the first fraction. Then we want to factor the bottom of the second one. Now the bottom of the second one turns out to be the easiest of any of these to factor. A squared minus 2a, they just have a common factor of a. So once we've factored everything, that's what it looks like. Now here we've got a fraction divided by another fraction, so we're going to flip the second one and multiply them. So on the top, I'll have a plus 2 times 5a plus 2. When I flip it, I'm going to be multiplying by a times a minus 2. On the bottom, I'll have the a minus 2, the a plus 2, the a squared plus 4. And when I flip the second fraction, this 5a plus 2 squared becomes on the bottom. And then what I've got to do is just cancel everything I can cancel. This a plus 2 cancels with that a plus 2. This 5a plus 2 cancels with one of those guys. This a minus 2 cancels with that a minus 2. And what's left in the end here is just a over a squared plus 4. So, yes?
And then also have one of the 5a plus 2 at the bottom.
Oh, yeah, thank you, thank you, thank you. Yes, that one of them didn't cancel. Yes, I was thinking, oh, the 5 has 2 canceled, but only one of them did. Yeah. Yes, Kath?
I was thinking on the actually the A for plus 4 type equation, but sometimes we would expand that and then subtract the A that is created by that. You would know it's supposed to.
Oh, like expand this thing? No.
Just the A plus.
Oh, this, a plus 2 times a squared plus 4. Oh, I'm trying to see when it's, so it depends what your goal is for doing with this. If we had this, and these guys cancel, then yes, you might want to expand what's left. Expanding things, now, actually, you know what? I will talk about this maybe with the next example. Oftentimes, now, when you're dealing with rational expressions, you don't usually want to expand things. But there is one time when you do, which is when you have two different rational expressions being added or subtracted from each other, and the tops of those two are already factored. Because when you're adding polynomials in general, oh, here's the other thing you might have seen. If there was this thing minus something else that also had an a minus 2 in it, and we take that a minus 2 out of a common factor, and you've got this guy left. So there are situations in which that will come up when you want to expand things. With rational expressions specifically, if you have two, if you're adding or subtracting them and the numerators are already factored, then you will need to expand those numerators so that you can collect like terms. I haven't actually given you any problems like that, I don't think, where we've got numerators that are factored and you need to expand them. Oh, at the end of the course today, we will see something, well, we won't expand it. I will say that, actually in that particular situation, expanding isn't usually useful, but yeah, you will see some examples where there are situations where you do need to expand things later. But the moral of the story is usually when dealing with rational expressions, you don't, and I will sort of show you some exceptions later. That's sort of the, yeah. Okay, so that was sort of how you divided rational expressions in the last example. The next thing you need to be able to do is to add and subtract them, right? How do you add and subtract rational expressions? Well, that's when you need to find what's called a least common denominator. You can basically make the denominators the same, make the bottoms of those fractions the same in order to add or subtract them. The least common denominator is always the smallest possible denominator, which has every single factor that occurs in the rational expression. We factor all of the denominators, we compare those denominators and take the smallest thing which has every single factor in it. And then we've got to multiply the top and bottom of each rational expression by something to make those denominators the same. So here's an example of one which we can do that sort of approach with. Oh. Here we have 12x over 2x plus 1 minus 8 over x squared plus 2x plus 2 over x. So now our goal is to make all those denominators the same. Here we've got 2x plus 1, here we've got an x squared plus 2x, here we've got a 2 over x. But what I'm going to do first is I'm going to factor all of them. Well, 2x plus 1, I cannot factor that. well, yeah, I could sort of try to factor out a 2, but then taking a 2 out of a 1 will leave with a 1/2, which is not useful. Here, x squared plus 2x, if I factor that, that's x times x plus 2. Right? Those two guys have a common factor. And here we just have 2 over x. So our goal now is to see, okay, what's the smallest thing that can make all those denominators the same? Well, that least common denominator, which we call the LCD, it has to have a 2x plus 1 in it. It also has to have an x in it. It also has to have an x plus 2 in it. It also has to have an x in it, but there already is an x in it as a factor. So I don't need to put another x in. I already have a factor of x. So that's what I'm going to try to make all those denominators equal to. I'm going to try to make all the denominators be the same as this guy. So for the first one, I'm going to have to multiply the top and bottom by x times x plus 2. To make those denominators the same. For the second guy, I'm going to have to multiply top and bottom by 2x plus 1, because that's the thing that's missing from this one. And on the last guy, I'm going to have to multiply top and bottom by both the 2x plus 1 as well as the x plus 2. Okay. So now, what I need to do is I need to basically, okay, now I've made the denominators the same. Now this cat is one of those situations where we do need to expand the numerators. I am going to need to expand this guy, I'm going to expand this guy, and I'm going to expand this guy. And the reason why is because what I'm going to have to do next, I'm going to have to take this thing minus this thing plus this thing. I cannot add and subtract polynomials until they've been expanded. So, so 12x times x is 12x squared. Actually, yeah, I'm just going to do it as 2 separate steps. So here it's going to be 12x squared times x plus 2. I'm going to need to expand it a little bit more later. This one's going to be 16x plus 8. And the last one is 2 times 2x plus 1 is 4x plus 2. And I'm still going to have to multiply that 4x plus 2 times the x plus 2 here. And all the denominators are now the same. X plus 2, 2x plus 1, x plus 2, 2x plus 1, and x plus 2, 2x plus 1. So now that all the denominators are the same, what I can do is I can add or subtract the numerators. I can take this guy minus this guy plus that guy. And so we're going to write this up top here. So 12x squared times x plus 2 is 12x cubed plus 24x squared. Oh boy. I need more space than that. 12x cubed plus 24x squared minus 16x plus 8. I've got a minus 16x and also minus the 8. Again, if you have a minus sign in front of a long expression, you've got to apply the minus sign to both things in it, both the 16x as well as the 8. 4x plus 2 times x plus 2 is going to be 4x times x is 4x squared. 4x times 2 is 8x. 2 times x is 2x. And 2 times 2 is 4. Oh boy, I just barely squeezed that in. And the bottom will still be x times x plus 2 times 2x plus 1. So that's what we get. We expand each of those things in the top. We get that complicated thing on the top all over that denominator. And then the next step is to simplify everything that's on the numerator, to collect like terms, we call it. So 12x cubed, there's no other x cubes in there, that's just going to stay as it is. Here we have a 24x squared plus 4x squared. That gives you a 28x squared. We've got a minus 16x plus 8x plus 2x. Minus 16 plus 8 is negative 8. Negative 8 plus 2 is minus 6. And then we have a minus 8 and a positive 4. which gives you a minus 4. Over x times x plus 2 times 2x plus 1. And usually we just leave it like that. You can try to factor the thing in the numerator, but it's not worth it. Factoring that's going to require too much work. It's not really worth it. Fine, fine. So our goal is basically just to expand the numerators here, collect like terms, and then stop. And also you'd never want to expand the denominators. You always want to keep the things on the bottom factored. It's only the numerators on the top where expanding is sometimes worthwhile. Yes?
Is that 20x to the power of 4?
28x to the power?
Oh, yeah. That one.
Yeah, x to the power of 4. So, yes, because there's a 4x squared. Oh, yes, should be an x squared. Thank you.
Okay.
Sorry, no, it was an x to the 4. It was not right. It shouldn't have been an x to the 4. I thought you were asking me about like my writing, and it wasn't clear enough. No, it's supposed to be an x squared. Thank you. Because x squared plus x squared gives you 2x. Yeah, it's still give me an x squared. So again, this is a sort of a harder type problem. There is one that's this difficulty on the webassign, I believe, on the quiz, because you only have 15 minutes to do the entire quiz. I'm not going to give you anything this difficult because it would take too long. But this something this difficult could come up on the test, could come up in the exam. So yeah, being able to work with things like this is important. Any questions about this one? Okay. So, what can be even more complicated is what are called complex rational expressions. Complex rational expressions are rational expressions in which the numerator and the denominator are each themselves fractions. So you have fractions on the top and fractions on the bottom. Simplify such a complex rational expression, what we usually do is we simplify whatever's on top, we simplify whatever's on the bottom, and then divide whatever we get on the top by whatever we get on the bottom. So here's an example of one. X over y squared minus y over x squared over 1 over y squared minus 1 over x squared. It turns out that even though this problem looks harder than the one we just did, it actually won't take as much board space or as much time. Because it's actually, takes a few fewer steps. So here we have x over y squared minus y over x squared all over 1 over y squared minus 1 over x squared. So our first goal is to put things over, yes?
All that then after, isn't it? Draw back to plus 20x minus 10x.
You said minus 16 plus 8 plus 2.
Oh, no, wait.
Yeah, minus 16 plus 8 plus 2 should give me minus 6, yeah. Thank you. Yeah, but thank you for asking about it because I have made mistakes like that before. Yeah. So here, our goal is to, on the top, make these two denominators the same. Make the y squared and the x squared the same. Well, they don't have anything in common, so I'm just going to multiply the top and bottom of this one by x squared, and the top and bottom of this guy by y squared. Right, and the denominators will both be x squared, y squared. Same thing here. I want to make these two denominators the same. We multiply top and bottom here by x squared, top and bottom here by y squared. So what am I going to get once I do that? Well, here x squared times x is x cubed, minus y squared is y cubed. And again, those denominators are both going to be the same. It's both going to be x squared, y squared. On the bottom, x squared minus 1 times y squared is y squared. And the denominators are both going to be the same. X squared, y squared. And now since we have a fraction divided by a fraction, we flip the bottom fraction and we multiply. X cubed minus y cubed over x squared, y squared times, if I flip the second one, x squared, y squared over x squared minus y squared. Now a couple things to mention at this point. First, these x squared, y squareds are going to cancel with each other. Diagonal cancellation is allowed as long as you're multiplying fractions. If you're dividing them, you can't diagonally cancel like that. If you're multiplying them, you can. The other thing to mention is that these guys, x cubed minus y cubed and x squared minus y squared, we're going to want to factor those. Because if we factor those, it will become a little bit more obvious how we might be able to cancel. So, there's a formula for factoring x cubed minus y cubed. It was a few slides ago, and it is this. X minus y times x squared plus xy plus y squared. When we factor x squared minus y squared, it's going to be x minus y times x plus y. Which means the x minus y's are going to cancel. And my final answer is just going to be x squared plus xy plus y squared over x plus y. One thing to mention about this particular problem is one of the ones where the final answer is significantly simpler than what we started with. There's no extra ugly fractions, there's just sort of simple polynomial over another polynomial. And there's no square, oh, there's some squares here, but there's no squares in the polynomial. So, yeah. Yes?
So at that point, the third step, or the step before the last one here, would it be wrong if I took out the x squared minus y squared and kind of simplified it that way?
Oh, like took out as in like
Yeah,
factor this guy?
thing.
Factor this guy?
Yeah. Like, take x squared and y squared, and you'd be left with x minus y is. Like if you put those together into one.
No, you cannot. This does not factor as x squared minus y squared times x plus y. This does not factor like that.
Okay.
You multiply this out, this will give you x cubed. X squared times y is x squared y. Y squared times x is y squared times x. Those terms will not cancel.
Okay.
So this is not allowed. X cubed minus y cubed does not factor this way. It factors this way. And that's the only way to factor x cubed minus y cubed. If you take this other one, you try to multiply it out, it will, yeah. Yeah, because I was like, how are you getting x plus y? You know, yeah. Yeah. If it was x to the fourth minus y to the fourth, it would be x squared minus y squared times x squared plus y squared. Because they're both even powers. If they're both even powers, you can use the x squared minus y squared rule. If they're odd, you have to use other rules. Yeah. And I've taught you the one for x cubed minus y cubed a few slides ago.
Okay.
For fifth powers, for seventh powers, there are rules that you don't have to use them. But they do exist for other odd powers. Okay, any other questions about this guy? Okay. So the last thing I'm going to talk about for today, now I'm definitely behind schedule, so there will be a little bit of time for group problem at the end, but it won't be much that I'm expecting. Is what are called fractional expressions. Fractional expressions are things which look like rational expressions, except they're even more complicated because they've got square roots in them, or they've got powers in them, or something like that. Now, you will only ever have to deal with very specific types of these sorts of expressions, and these specific types of fractional expressions are exactly the ones that come up in calculus. So that's what I'm going to be teaching in section 1.3.4, is a couple situations that come up in calculus that are even more complicated than what we've seen already. How many people, so one of the situations is rationalizing the denominator of something like this. In other words, not just a square root on the bottom, but it's a difference of square roots on the bottom. Has anyone seen these sorts of questions before? Rationalizing denominators in that situation, like see 1, 2. Is there anyone who has, yeah, okay. I guess there's a few people, but most people I'm assuming have not seen this before. How many people have not seen this sort of thing before? Put up hands if you haven't seen it. Okay, I haven't seen people who specifically say they haven't seen it. Anyways, it is something you will be using in calculus. The rule we're going to use to rationalize denominators like this, again, when we had something just a square root of x in the bottom, we could just multiply top and bottom by square root of x to get rid of it, right? If we have something like square root of x minus square root of y on the bottom, what we're going to have to do is we're going to have to multiply top and bottom by what's called the conjugate of that thing. If we have square root of x minus square root of y, the conjugate of that is square root of x plus square root of y. And the reason this conjugate is useful is because of the following rule, right? If we have x minus y times x plus y, that always gives you x squared minus y squared, right? That's one of the formulas we talked about earlier. So if I have square root of x minus square root of y times square root of x plus square root of y, it's going to give me square root of x squared minus square root of y squared. What's square root of x squared? X. What's square root of y squared? It's just y. So the thing is, if we have this in the denominator, we multiply it by this guy, it turns out it'll basically get rid of the square roots. So if we ever have something that looks like a minus b in the denominator, we multiply it by a plus b, whatever those a and b's are, it'll rationalize it, it'll get rid of the square roots. Similarly, if we have something that looks like a plus b, we multiply it by something that looks like a minus b, it'll also get rid of the square roots. That thing that you're multiplying by is what's called the conjugate. Now, you can have problems where it asks you to rationalize the denominator, also problems where it asks you to rationalize the numerator. Basically, the part you want to rationalize is whatever part has two different square roots in it that are added or subtracted from each other. Now, I'll start example 10 over here. I can use those formulas on the board. So example 10, we have square root of x minus square root of x plus h over h square root of x square root of x plus h. So we want to rationalize the numerator. We want to make this thing on top into just something with no square roots in it. So what we're going to do is we're going to multiply top and bottom by square root of x plus square root of x plus h. So what we get, on the top we've got square root of x minus square root of x plus h plus square root of x plus square root of x plus h. So the thing we started with, here's what we're multiplying by. On the bottom we'll have h square root of x plus h times square root of x plus square root of x plus h. Multiply the same thing on the top and the bottom. And then when we do that, we can expand the thing on the top. Square root of x times square root of x just gives you x. Square root of x times square root of x plus h gives you positive square root of x plus h. Square root of x plus h times square root of x gives you the negative of the same things. Those two guys are going to cancel. And square root of x plus h times square root of x plus h gives you negative x plus h. Basically, I'm using the a minus b times a plus b rule. I'm going to take a squared minus b squared. A squared is x, b squared is x plus h. On the bottom, I've got the same thing. H squared of x plus h, square root of x plus square root of x plus h. And then I simplify the top. X minus, so basically minus x plus h is the same thing as minus x minus h. That gives you a negative h on the top. And then those h's will cancel. And we're left with negative 1 over square root of x plus h, square root of x plus square root of x plus h. Again, the thing we've got at the end is still ugly. It still looks weird. The situation you'll be using this in calculus is a situation where your goal is to make those h's cancel. In calculus, that's really part of your goal, is to make these h's cancel so that if I plug in h equals 0, I will get a fraction that works. I will get no zeros in the bottom of the fraction. So that's sort of the goal of what we're doing here, is to get those h's to cancel. And it turns out in this situation, to get the h's to cancel, we have to do this thing where we rationalize the numerator. We multiply top and bottom by that conjugate thing to make this numerator into something that has no square roots in it. Any questions about how this rationalization works? Okay. So last slide for today, which deals with what are called complex fractional expressions. Expressions that come up which have various polynomials, various powers on both the top and bottom of a fraction. They look fairly ugly. It turns out there's not much simplification you can do with things like this. The first thing you can do is if you've got two separate ones, find a common denominator for them, put them together. The second thing you can do with these sorts of things is look for common factors. Look for factors that occur in every single numerator and take those out as a common factor. Once we've done those two steps, once we've found a common denominator and we've taken out any common factors, then we can begin to expand the numerator and denominator, and only then. So here's an example of something that is fairly ugly like this. And again, the reason I'm doing these ugly things is because they will come up in calculus. And you will need to work with them. Again, these particular problems are more difficult than what you'll see on the quiz, but they could come up on test or exam. And there are ones like on the web assignment, I believe. So here we have x squared plus 9, all to the fourth, times negative 1/3, times x squared plus 6, to negative 4/3. Okay, sorry, I'm going to need the whole top of the board to write this out. Plus x plus 6 to the negative 1/3 times 4 times x squared plus 9 cubed times 2x. Now the first thing to mention here is that this thing looks really ugly. One thing to mention is we've got negative powers here. Negative powers are the same thing as a positive power in the denominator. So really we can think of this first thing as this guy over x squared plus 6 to the 4/3, right? This negative 4/3 can be written instead as a 4/3 in the denominator. Similarly here, this negative 1/3 I can instead think of as x squared plus 6 to the 1/3 in the denominator. So then I've got two different fractions, basically. And I want to put those fractions together. So I'm going to make those denominators the same. Now you notice it's the same thing in both denominators, but they've got different powers. So if I want to make those powers the same, I've got to add something to this 1/3 power to make a 4/3 power. 4/3 is actually 1/3 plus 1. Yes? I
How
move.
did that become x squared?
Oh. Ah. It should have. Oh no, it was no. This is the mistake. This is supposed to be an x. This is supposed to be an x. This is supposed to be an x, and this is supposed to be x. Thank you. Yeah, it was x plus 6 in the original. I turned it into x squared plus 6 for some reason. Yeah, it just should be x squared plus 6. But yeah, they should be the same thing. I want to make these powers the same. What do I have to add to 1/3 to get 4/3? I have to add 1. Right? 1/3 plus 1 gives you 4/3. I have to add 3/3, which is 1. So I'm going to have to multiply top and bottom here by x plus 6 to the 1. So I've got to do it on the bottom. I've also, on the top, I've got to multiply it in x plus 6 to the 1. So let me just write out the next step before I do anything more. So here I have x squared plus 9 to the 4th, negative 1/3, all over x plus 6 to the 4/3. Here I will have x plus 6, a 4, and x squared plus 9 cubed, and a 2x, all over that same thing. X plus 6 to the 4/3. And then what I need to do is I need to notice there is a common, these two things have a common factor. Oh, sorry, the first thing to mention, I'm adding together fractions of the same denominator, so I'm basically adding together the numerators. And these numerators have a common factor. This one has an x squared plus 9 to the 4th. This one has an x squared plus 9 cubed. Right? So they both have x squared plus 9 cubed in them. And so if I take an x squared plus 9 cubed out of this first guy, what I'm left with is x squared plus 9 times negative 1/3. If I take an x squared plus 9 cubed out of the second one, what I'm left with is an x plus 6 times 4 times 2x. And the bottom of this fraction is just going to be that common denominator, x plus 6 to the 4/3. So again, looks really ugly. But we've done, basically, made the denominator the same, we've taken out a common factor. Once we've done that, then and only then are we allowed to expand what's inside the bracket. If we try to expand earlier, what will happen is it's going to be really ugly, it'll take up more space than the entire board. But now that I've taken out a common factor, and then simplify what's in the bottom. Then I'm going to expand what's inside the brackets, collect like terms. And sadly, I'm going to have to erase what's on the top of the board and continue up here because there's no other space. So, x squared plus 9 times, first, the x squared plus 9 cubed, still going to be on the top there. The x plus 6 to the 4/3, still going to be on the bottom. X squared times negative 1/3 is negative 1/3 x squared. 9 times negative 1/3 is minus 3. X, so here 4 times 2x is 8x. 8x times x is 8x squared. 8x times 6 is 48x. And one more step. These two terms are like terms, I can combine them. 8 is 24/3. 24/3 minus 1/3 is 23/3. So the final answer will be x squared plus 9 cubed, 23 over 3x squared plus 48x minus 3 all over x plus 6 to the 4/3. So that's what we end up with at the end. And I apologize again, I only have 5 minutes left to do group problems, and I'm aiming for 15. Any questions about this before I show you those group problems? Okay. Okay. So again, this is sort of the most complicated problem you will see from this section. You will not see this on the quiz. Again, it takes too long to do. The quiz questions are going to be shorter questions, but again, I think there's one like it on the web assigned. So here's the group problems for today. Factoring this polynomial simplified expression. Again, try for the next 5 minutes. Oh! I never gave out the index cards for the muddiest points. Anyways, here, take one, pass them back. Take one, pass them back. And again, if you can write down the most confusing thing you found today, anything you want me to go over before the quiz on Tuesday, please do so. There is a quiz at the beginning of class on Tuesday. Again, I'm going to do muddiest points first and then the quiz. And there is the web assignment due Monday night. So make sure you do both of those. Both do the online assignment, it's due Monday night, and get ready for the quiz that's on Tuesday. And if you have any questions about these problems in the next 4 minutes, actually I will stick around till people leave. If folks want to stick around after 3:50 to finish these, I will stick around, but you're free to go in 4 minutes if you want, once you've worked on these problems. Did I just give this same problem twice again? I think I did. I think number 1 was one of the ones I did as an example, and I really thought I checked that when I was typing these up. Oh well, I apologize. You don't have to do number 1. You already have it as an example. Just do number 2. Yeah. I really thought I checked that. Anyway. Oh, where's my little box? Here. As you're leaving, please throw your cards in the box here. Oh.